This is the third lecture in the series of preliminary lectures, sort of prequels to the topics that we are going to study in PH3203 Advanced Quantum Mechanics. In the previous two lectures, we had met the Schrodinger Equation for the harmonic oscillator. We have seen some mathematical details behind how these equations are solved. We had met the Hermite polynomials. We had also studied various mathematical properties of the Hermite polynomials. In this lecture, we will begin with a recapitulation of these results, and then we will show you how to use these mathematical results to find out various physical properties. In the later half of these lectures, we are going to take a deeper look at the harmonic oscillator wave functions and try to understand why they behave the way they do from other, more general principles of quantum mechanics. Let me quickly summarize the mathematical results so far. We have seen that the Hermite polynomials can be written down in terms of something called the Rodrix Formula, where we do an nth derivative of the function e to the minus z square and multiply the result by e to the z square times minus 1 to the n. We have argued before why this should be a polynomial of degree n, and it's pretty easy to see that this is going to give rise to 2 to the n as a coefficient of the leading power. Another important mathematical result that we had talked about is the generating function for the Hermite polynomials, which essentially is a function of two variables t and z. This particular function, e to the 2tz minus t square, which if we were to treat this as a function of t alone and expand this out in powers of t, will definitely give you coefficients which are functions of z, and the coefficients apart from this 1 by n factorial factor turns out to be the Hermite polynomials of degree z. After finding the Rodrix formula and the generating function, we use them to determine some very important recursion relations for the Hermite polynomials. There are several ways in which you could write the recursion relations, but these are two which turn out to be very important. One which tells you that the derivative of the nth Hermite polynomial is essentially the lower order Hermite polynomial times 2n. And the other recursion relation allows you to write down a Hermite polynomial of any given degree in terms of Hermite polynomials of the next lower and the next to next lower Hermite polynomial. That is, hn plus 1 can be expressed in terms of hn and hn minus 1. Of course, this means hn can be represented in terms of hn minus 1 and hn minus 2, given, of course, n is greater than or equal to 2. We will use this later to be able to plot the Hermite polynomials using the gnuplot plotting system. And the final important result that we had, and the one which we are going to use extensively, is orthonormality. This is the result that if you multiplied two Hermite polynomials hnz with hmz and multiply this product with an extra weighting factor e to the minus z square and integrated all the way from minus infinity to plus infinity, you will get 0 whenever m and n are different, and when m and n are equal, the result you are going to get is 2 to the n times n factorial times square root of pi. Let us now see how we could use the mathematical properties that we have outlined right now in order to figure out various important physical results from quantum mechanics for the simple harmonic oscillator. In particular, well, let's start with the energy eigenfunctions for the harmonic oscillator. As we had already figured out earlier, the nth energy eigenfunction for the harmonic oscillator, expressed as a function of the dimensionless variable z, is given by the nth Hermite polynomial of z times e to the minus z square by 2 up to an overall constant, which is the constant for normalization. Let us first try to figure out what this normalization constant is going to be. Of course, for this, what we need to do is impose the normalization condition, which is, if you were to take the mod square of psi and z and integrate from minus infinity to plus infinity, you are going to get plus 1. Now, since in this expression, apart from a, everything else is guaranteed to be real, all we need to do is simply square this and integrate, and you end up with a mod square times this integral equals 1. This is exactly the integral in the orthonormality condition that we met a while ago for n equals m. So it's pretty straightforward to figure out that the normalization constant a actually obeys this equation. This is just the value of the integral from our orthonormality condition, which we talked about a while ago. And this immediately tells us what a mod is going to be, the square root of the reciprocal of this. And we can just take this a mod and plug it in the expression for the wave function and figure out that the wave function is going to be this up to an overall phase factor. Remember, a mod is what we get, not a. So you could have an arbitrary phase factor here. Since an overall phase factor does not really have any physical significance, we have just decided to omit that in this expression. So we finally end up with psi nz equals hnz e to the minus z square by 2 divided by the square root of 2 to the n factorial root pi. So this is our normalized nth energy eigenfunction, but this has been normalized using the variable z. Using the dimensionless variable z for doing various calculations actually makes life rather easy for us, because some of the nasty factors made out of h cross, m, omega, etc. can be completely ignored in this way of doing things. Of course, at the end of the calculation, when you want to find out things like expectation value of, say, x square, what you do is find out the expectation value of z square and then supply the appropriate combination of h cross m omega, or basically supply whatever connecting relationship you have between z and x to find out x square's expectation value. Not really a difficult thing to do in the end, and actually that's the neatest way of doing the calculation. But just to show you how we would actually approach this calculation if we were using the original variable x, let me just repeat this calculation quickly for you for the normalization. If instead of normalizing the wave function as a function of z and demanding the integral over all z gives you 1, I'd actually use the real wave function, or real in the sense that wave function which is a function of x, and demanded that the normalization follows when you integrate over all of x. Well, first the wave function is going to be a normalization constant times the Hermite polynomial of nth degree with x as an argument, but you have to supply the extra root over m omega by h cross factor, which remember is a factor which made x dimensionless and turned it into z. So this really is just z, and here also in the exponent you have z square by 2. I have just expressed z in terms of x. So what I have really done is I have used this relationship between z and x to write down the wave function in the previous example entirely in terms of x. It might seem that this will lead to exactly the same results and a would turn out to be exactly the same, but there is a catch there. The catch simply is that the normalization condition now, in fact that is the standard normalization condition in quantum mechanics, is that when you integrate psi n of x mod square over all x, you are going to get 1. And why is this not the same thing as integrating psi n z square dz over all z? The answer simply is that dx and dz are different. They differ exactly by this factor, which is why this will lead to a slightly different value for the normalization constant. Anyway, the normalization constant can be easily figured out by working out this integral, and the obvious thing to do, if you did not already know that z is root over m omega by h cross times x, is to substitute root over m omega by h cross into x sitting here in terms of something else. So basically what we have done is we have just gone back to z here and we have done this integral. Exactly the same steps as before. The only new thing is, because of the relationship between dx and dz, you get an extra root over h cross by m omega factor. So your normalization constant actually is slightly different. It is 1 by root over 2 to the n factorial, fourth root of pi, but in addition there's also fourth root of m omega by h cross which comes in because of this extra factor here. So the nth order energy eigenstate in terms of the position variable x and fully normalized is given by this expression. Let us now quickly go through a couple more applications of these mathematical results to problems in quantum mechanics. And in these, what I'm going to do is I'm going to use psi n of x as a wave function rather than psi n of z. It should be easy enough for you to figure out how you would proceed if you were using psi n z. In fact, the calculations would actually end up looking simpler if we were using psi n z, because these factors or factors like these will not really show up there. Of course, in the end, you would have to supply back appropriate powers of alpha to be able to connect with the actual results that we are getting here. Anyway, let's go ahead and try to first calculate the expectation value of x, which of course is nothing but psi n mod square x dx integral from minus infinity to plus infinity. Now, even without evaluating this integral, I know that this integral must vanish. Why? Because we know that the energy eigenfunctions have to be either even or odd, and in either case, psi n square has to be an even function. So x times psi n square has to be an odd function, and the integral of an odd function from minus infinity to plus infinity, or from any limit minus a to plus a, must be 0. So we know even before we start doing the calculation that expectation value of x must be 0. Let us just pretend, however, that we have not been able to spot this obvious thing. So what we are going to do is we are going to pretend that we don't know that expectation value of x is bound to be 0, but we are going to try to use the explicit form of the wave function and the properties of the Hermite polynomials to figure out that it's going to be 0. So how do we do that? We of course first put in the wave function. So this is the mod square of the normalization constant, and then you have hn square e to the minus m omega x square by h cross times x dx. Once again, the only way in which you can actually evaluate this integral, of course without having spotted the obvious thing that this is 0, is to substitute root over m omega by h cross times x equals z, and once you do that and take care of the normalization constants properly, you are going to end up with this result. I'm not going to explain where this factor comes from. It's pretty easy to figure it out just by doing this correct change of variables. But the integral here is z times hn z square e to the minus z square dz. Once again, let's pretend that we can't see that this integral has to vanish because of the fact that it's an integral of an odd function over symmetric limits. Let us just try to see how we could use the orthonormality relation and the other properties of the Hermite polynomials to figure out that this is going to vanish. But you can see that you cannot directly use the orthonormality relation here, because this is not hnz hmz times e to the minus z square. There's a third factor here, which is z. But we have this recursion relation between Hermite polynomials. And this tells us that you can write down z times hnz in terms of hn plus 1 and hn minus 1. And we do precisely that. We keep one of the hn factors outside and replace the other factor z hn by this thing in the bracket here, half hn plus 1 plus n hn minus 1z. And now this integral is one in which you could definitely use the orthonormality relation. Hn z hn plus 1z, two different n and m's here. So this must vanish. Here you have hn and hn minus 1. Again, n and m are different. So from the orthonormality relation, this must vanish. So you have a value of 0 for this expectation value of x for the nth eigenstate. Now, having established this completely trivial result, using some non-trivial gymnastics with recursion relations and orthonormality, let us now try to see a case where these techniques will give us a non-trivial result. For this, all we have to do is take a look at how to calculate expectation value of x whole squared, which of course is psi n mod square x squared's integral, and substituting the nth energy eigenfunction leads to this expression. I will leave you worry about whether the factors in front are okay, but that should be easy enough to check. And once again, with the standard substitution, standard by now, that is root over m omega by h cross x z, this is what you are going to get. Once again, you should convince yourselves that the factor in here have been calculated correctly. Now that you have this, what would you do? Well, there are several ways of proceeding here, but one way is simply to start with whatever we took in the previous calculation. That is, zhn z is given by a combination of hn plus 1 and hn minus 1. And this thing here is just the square of that. So we just squared this expression on the right and substitute. Of course, squaring this and substituting gives rise to this thing in the bracket. Apart from the e to the minus z square, this thing in the bracket here is nothing but the square of this expression, 1/4 hn plus 1 whole square plus n squared hn minus 1 whole square minus n hn plus 1 hn minus 1 z. Now we can use the orthonormality relation not only in the cases where you have different n and m, but also when you have the same n and m, namely here and here. This one, of course, the term written in blue, involves two different Hermite polynomials, and this must vanish. So what you have here is that apart from these factors outside, you get 1/4 2 to the power n plus 1 factorial root pi. That's simply because the result for the orthonormality relation, of course, depends on n. So you have to use n plus 1 in place of n here. And similarly, you have to use n minus 1 in place of n in this expression, and you end up with this result. And the part in blue, of course, is 0. After this, all you have to do is cancel off appropriate factors of 2 to the n and n factorial. This, of course, will give you just 1, 2 and 1/4, so that's a half n plus 1. That's nothing but n plus 1 factorial by n factorial. Similarly, here n times n minus 1 factorial already given n factorial. That's an extra n, and dividing the 2 to the n minus 1 by 2 to the n will give you a by 2. So combining everything together, you are going to get h cross by m omega n plus half as the expectation value of x square. This should be a pretty familiar result from your previous courses, but I would urge you to try to think of other ways of calculating this result, and as an exercise you could definitely figure out what the expectation value for p square would be using the Hermite polynomials and their recursion relations. Of course, since p involves a derivative with respect to x, it's obvious that you would rather use the hn prime recursion relation and use that to figure out what expression value of p square is going to be. So far, we have explored some of the mathematical properties of these Hermite polynomials and used these properties to establish a few important physical conclusions. However, it would be much better for us to understand what's going on if we could have a visual picture of these polynomials and the associated wave functions. And that is what we are going to turn to next. Of course, you have seen plenty of these figures in your quantum mechanics textbooks, and you have definitely met them in your earlier courses. All I am trying to do is try to explain how you could actually visualize these wave functions using software tools that are available to you. So what do the Hermite polynomials really look like? To understand that, let me just plot some graphs for you of the Hermite polynomials using the gnuplot plotting software. And for this, what we are going to do is make use of this recursion relation between Hermite polynomials that we have. This will be able to tell us what a given Hermite polynomial is if you know the two previous Hermite polynomials. In particular, what I will do is write this as hnz is equal to 2z hn minus 1z minus twice n minus 1 hn minus 2z. But this alone will not tell me the Hermite polynomials, because what I need to know is at least two pieces of information in addition to this. That is, what is h0z, and we know that that's 1, and what is h1z, that of course is 2z. So once we know these two things, I can use them to find out h and z using this recursion relation. So how do you do this in a programming language? You can use recursive definitions, and gnuplot also allows you to define a function recursively. Let us see how that goes. So let me start gnuplot, and then what I will do is I will define this function h with two arguments, n and x. Gnuplot always takes as independent variable the one it plots along the horizontal axis as x. So you cannot call it z even if you wanted to. But how do you now define this? You define this by using something called a ternary operator in gnuplot. And the ternary operator essentially allows you to ask a question and give more than one option based on the answer. And it's really very easy. What you really do is something like this. You ask first whether n is 0 and equal to 0. The equal to sign is always double equals, because a single equal to sign is obviously used for assignment, as you can see. So you are asking this question, so you end with a question mark. And after that, what you put in is what happens when the answer to this is yes. So of course, if the answer is yes, you put in 1. If the answer is no, what you do is put in, well, you don't know what to put in right now. If the answer is no, then all you know right now is that n is not 0. So next you ask, is n 1? That question gets asked again. And now, if the answer to that is yes, you put in 2 into x. That's what h1z is. And if the answer to that also is no, now I know that n must be more than 1. And for that, this particular recursion relation will work. So then h and z is going to be 2 times x times h with n minus 1 and x as arguments, minus 2 times n minus 1 times h with n minus 2 and x as arguments. This is how you define the Hermite polynomial function in gnuplot. At least one way. This is how you do it using the recursion relation that we have written down. Does this work? Let's see. Just for convenience, I set 0 axis so that I can have graphs in which the x equal to 0 and y equal to 0 axes are drawn. I will increase the number of points used to draw the graph to, say, 10,000 from the default 100, simply so that we can capture the oscillations, etc. nicely. And let us now do one thing. Let's plot from minus 5, x equal to minus 5 to x equal to plus 5. Let's say the fifth Hermite polynomial. And this is what the plot looks like. Unfortunately, the plot doesn't really look very impressive. Okay, let me just do one thing first. Let's increase the line width to, let's say 3, so that you can see the line a bit thicker. Okay, so the line is thicker now. You can see the Hermite polynomial, but you can hardly make out any structure. And more importantly, as you can see, both as x becomes very large, in this case just plus 5 and minus 5 on this side, you are ending up with a huge value for the polynomial. And it's obvious that the polynomial is going to diverge away to infinity, as polynomials should, as x goes to plus minus infinity. Since gnuplot uses auto-scaling, the y scale has been set so high that any structure you had in this region simply is invisible. But it may be a better idea not to plot h5x, but to plot the wave function that you expect here. Remember, this x is our dimensionless z. So what you really should do is multiply this by x square by 2, e to the power minus x square by 2. And now plot this. Now you can see the familiar wave function like structure. This is the wave function like structure that you get for the fifth energy eigenstate. And you can see here that you have 5 places where you have zeros. Since we are going to plot the wave function several times, it may be a good idea at this point to define a function which will directly give me the wave function. And it's good to have the normalization in place so that we can compare different wave functions in the same scale together. So just to remind you, the normalized wave function is given by this expression, the nth normalized wave function, psi n z is 1 by root over 2 to the n factorial root pi. Then you have h and z, and then you have the minus z square by 2. So this is the expression for the normalized wave function, and this is what we are going to now define in gnuplot. To do that, we define the function psi of n and x to be equal to what else? H n comma x times exponential minus x square by 2, and then divide it up by the normalization factor. The square root of 2 to the power n times square root of pi. Pi gnuplot recognizes as pi simply, times the factorial of n. Now gnuplot does not have a factorial function, but it actually has something better. It has a gamma function inbuilt into it. So you could use the fact that gamma of n plus 1 for an integer n is nothing but the factorial of n. So I hope I have closed all the brackets that I had opened. Let's see. Yeah, I have. Otherwise this would have given rise to an error. So let's try plotting the wave function for the ground state now. So x going from minus 5 to plus 5 as before. I just say psi 0 comma x. And this is what the wave function looks like. It would be better if I actually plotted this with the y scale, put y range also put in, and with a line width of 3, let's say. And there you have it, a nice Gaussian as expected. Now, not only can you plot one wave function at a time, you can of course plot several curves at a time. Just to remind you, all you need to do for that is just separate the different functions you want to plot with a comma, and now you have the ground state and the first excited state plotted together. Just to point out to you, okay, let me just make this full screen. Just to point out to you, the ground state is an even function which has no nodes. Of course, it has nodes at the two very ends. They're not really called nodes technically, but they are zeros of the wave function. Whereas the first excited state is an odd function, as you can see, has one node in the middle of the range. In fact, it has a node exactly at 0. Fine. So let's return back to my gnuplot terminal and let's just put in a few more wave functions at the same time. Let's plot psi 2 comma x, line with 3, and psi 3 comma x. So the first four energy eigenfunctions, the ground state and the first three excited states, are being plotted together here. I could, of course, use the for loop which gnuplot has for I equals 1:3 kind of structure to actually do the job for me. But I just wanted to write the whole thing out anyway. And here is your first four wave functions of the harmonic oscillator, first four energy eigenfunctions plotted together. Let me just point out some basic features. As you can see, the wave functions are even and odd in succession. The blue one here is psi 0 of x. You can read the legend on the side. It will tell you the psi 0 x is this blue, deep blue line. Actually, this is purple, perhaps. This purple line, that's even, nodeless, as we have seen before. The green, as before, is the first excited state. That's odd, has one node. The cyan or the light blue line that you see here, that's the second excited state. It has two nodes exactly in the finite part of the x-axis, and it's an even function. The orange is an odd function, and you can see that it has three nodes. Now, in what follows, we are going to explain some of these findings from a more mathematical point of view, but it is good to have a picture in mind when you're thinking about these things. Now, we have seen several interesting features of the energy eigenfunctions of the harmonic oscillator. One of the most striking features is that these wave functions are even and odd in succession. That is, one of them is even, the next one is odd, and so on. So can we understand this feature on more general terms? Why are the wave functions even or odd? Now this brings us to a very important concept, that of a symmetry of a wave function. This is going to play a huge role in subsequent parts. With parity symmetry, the one we are focused on right now, the thing is very elementary and easy to understand in very simple terms. So let us try to understand why is it that parity symmetry implies that the wave functions of the harmonic oscillator, or the energy eigenfunctions of the harmonic oscillator to be more precise, have a definite parity. That is, they are either even or odd. To understand that, let us first understand what this parity symmetry is at all. Well, the harmonic oscillator shares with many other Hamiltonians this particular property. Remember, for the harmonic oscillator, the potential energy is half m omega squared x squared. And that has this obvious property that if you were to replace x by minus x, you end up with the same value for the potential. Now the Hamiltonian, of course, has two pieces. It has the kinetic energy p squared by twice m. In addition, it has the operator corresponding to the potential energy. And p in the position representation, the one we are using right now, of course, is h cross by I ddx. Now when x changes to minus x, the derivative of course also changes sign. That's the simple chain rule. However, because the kinetic energy part of the Hamiltonian has p square, you end up with two minus signs, which means the kinetic energy part never changes under x going to minus x. The potential energy, whether it will change or not, will depend on what particular potential energy the system has. For our system, the harmonic oscillator, we have v minus x equals vx, which means for our system, h minus x is the same as hx. So when you write down the Schrodinger equation, you end up with this equation, of course. I've explicitly shown the x dependence of the Hamiltonian, which usually we don't write, but of course the Hamiltonian depends on x. So hx acting on psi x is the energy E times psi x. Now this is valid for all x. So one thing you can easily see, since it's valid for all x, this equation can also be written as h minus x psi minus x is E psi minus x. Strictly speaking, this is not the parity operation that we are doing here. All we have said is you have replaced x by minus x. The parity symmetry essentially tells us that hx is the same as h minus x. As a result, these two equations essentially have the same Hamiltonian sitting on the left hand side, which means hx acting on psi minus x must be the same as e psi minus x. So what does this tell us? It tells us that we have two equations. This one tells you that psi x is an eigenstate of hx with the eigenvalue e, and this one says that psi minus x is also an eigenstate of hx with the same eigenvalue e. The point is, if psi x is an energy eigenstate, so is psi minus x. And they correspond to the same energy eigenvalue. By the way, this will work in 3 dimensions as well. If you have a potential which obeys V of minus R is the same as V of R. So if the potential has the symmetry under inversion, which of course all potentials don't, but a very important class of potentials, the central potentials, do obey this particular property, because the central potentials of course depend only on the length of the vector R, and minus R and R, these two vectors of course have the same length. So for 3-dimensional problems with central potentials and other potentials which have this kind of symmetry, you do have H minus R is equal to HR. The kinetic energy part stays the same simply because the kinetic energy part involves two derivatives with respect to position, and two minuses always make a plus. So whatever we argued here will also work in 3 dimensions if you have a potential which is symmetric under the parity operation R going to minus R. So while we have said psi x and psi minus x are eigenstates of Hamiltonian corresponding to the same eigenvalue E, we could have generalized this to 3 dimensions and said psi R and psi minus R are eigenstates of H corresponding to the same eigenvalue E. Now coming back to 1 dimension, we have two possibilities here. One is that the eigenvalue E is degenerate, that is psi x and psi minus x are two independent wave functions corresponding to the same energy eigenvalue. If not, there is another option, which is psi minus x and psi x are not independent, they are actually proportional to each other, which means psi minus x is some constant times psi x. This of course doesn't count as a new wave function, simply because the Schrodinger equation being a linear homogeneous equation, if psi of x is a solution to that, any multiple is of course also a solution. So they are considered to be the same solution. So you have now two options, E being degenerate or psi minus x equals lambda psi x. Now we are going to make use of a very important result in 1-dimensional quantum mechanics, which is a theorem which says there is no degeneracy in 1D bound states. That is to say, if you have 1D energy eigenstates, okay, when I say bound states, I really mean energy eigenstates, that's important. So if you have eigenvectors of the Hamiltonian which die out far enough away from the origin, then such eigenvectors correspond to eigenvalues which cannot be degenerate. Now why that is true we are going to explore in a minute, but before that let me just look at the consequence of this theorem. According to this theorem, if we are looking at 1-dimensional bound states, which we are for the harmonic oscillator, this possibility that E is degenerate simply does not arise. So you must have this other possibility for the harmonic oscillator and for other parity symmetric potentials in 1 dimension. You cannot have degeneracy for bound states, and therefore you must have this result. The psi minus x is lambda psi x. This of course is again valid for all x, which means you can write this equation also for x going to minus x, which gives you psi of x is lambda times psi of minus x. This is just this equation with x replaced by minus x. But we know the psi minus x is lambda times psi x. So we end up with psi of x is lambda square times itself. And of course that leads to lambda square being 1, which means lambda is plus minus 1. In other language, Psi minus x equal to lambda psi x simply says that psi of x is a parity eigenstate as well. That is, if you carry out the parity operation which changes x to minus x, you end up with a function which is not a new function but a multiple of the old function. And what this is telling me is that the only two possible eigenvalues for the parity operator are plus and minus 1. Now that also is very easy to understand from the basic property that parity operation, if you call it P, if you do it twice, that is change x to minus x twice, you must get back to the identity. So any eigenvalue of the parity must obey this equation lambda square equal to 1, and hence lambda must be plus minus 1. So why are the energy eigenstates either even or odd? The answer simply is that energy eigenfunctions are parity eigenfunctions at the same time. This works for 1D bound states, and parity eigenfunctions have to be even or odd. Now before we go on to understand why is it that there are no degeneracies in 1D bound states, let me first quickly tell you what the scenario is in 3D. In 3D, a very similar result goes true. Of course, if V of minus R is V of R as I've said, then H of minus R must be H of R. And then the same result follows. That is, if psi of R is an energy eigenvector or eigenfunction with eigenvalue E, then so is psi of minus R. Now, not only are psi of R and psi of minus R eigenfunctions with the same energy eigenvalue E, any linear combination of these two functions, psi of R and psi minus R, also correspond to the same E. Now, the only catch here is that we no longer have the theorem which tells you that bound states are non-degenerate to help us out here, or to restrict us actually here. So it's very possible that psi of R and psi of minus R may be independent of each other. In fact, usually that is the case in 3D. So our argument that psi of R and psi of minus R must be multiples of each other, hence psi of R must be even or odd, that no longer works in 3D. However, because any linear combination of psi of R and psi of minus R also corresponds to an eigenfunction corresponding to the same energy eigenvalue, what we can always do is this. We can always define two eigenfunctions of the energy, psi E of R and psi O of R, by just adding psi of R and psi of minus R together in the first case, or subtracting one from the other in the second case, and this gives us two wave functions. Now the labels E and O are obvious because if you carry out parity on psi E, what you're going to get is psi of minus R and psi of R are going to get interchanged, but of course that doesn't change the sum. So you have parity acting on psi ER is psi ER with a plus sign. Parity acting on psi OR, on the other hand, has to be minus psi OR, which means that if you change the sign of R here to minus R, you're going to get minus R here, plus R here, a minus sign as a result. Now notice, although the original wave functions that we came up with, perhaps this psi of R and psi minus R, may not have been a parity eigenstates, may not have been either even or odd, we can always recombine them this way, and we can always choose the Hamiltonian eigenstates to be parity eigenstates. That is, we can always choose to use psi E of R and psi O of R as our energy eigenstates. So, whereas in one-dimensional bound states for a parity symmetric Hamiltonian, which essentially means a parity symmetric potential, the wave functions are definitely even or odd. In 3D, the result is you can always choose the wave functions to be even or odd. Because parity symmetry often makes life very simple for other calculations, we usually choose to do that. Remember, in 3D, this is a choice and not necessarily something that follows directly from the mathematics. But what follows from the mathematics is that such a choice can always be made. We will later see that this is a specific case of a more general result that follows whenever you have a Hamiltonian which has a symmetry. The next question is, why exactly are there no degeneracies in 1D energy eigenstates? The answer is this follows simply from the properties of the Schrodinger equation itself. And the proof of that is again pretty straightforward. All you do is to assume the contrary. So the proof is really by contradiction. What you do, of course, is assume that there is a degeneracy. That is to say, there are two wave functions psi1 and psi2, both of which satisfy the same energy eigenvalue equation for the same E and of course the same potential V of x. By the way, this in itself does not contradict the no degeneracy result, but what we are assuming here in addition is that psi2 and psi1, this ratio, is not a constant. This is what we mean when I say that there is a degeneracy. Psi1 and psi2 both satisfy the same Schrodinger equation and they are independent of each other. Now, given this equation, it's pretty easy to multiply the first one by psi2, the second one by psi1, and arrive at this result by simple subtraction. Psi2 psi1 double prime minus psi1 psi2 double prime is 0. But if that is the case, then it's easy to see that this result, this left hand side here, is psi2 psi1 prime minus psi1 psi2 prime's derivative. Just to sort of show you how this goes, psi2 psi1 prime's derivative is psi2 psi1 double prime plus an additional term which is not there on the left hand side here, which is psi2 prime psi1 prime. But by taking a derivative of psi1 psi2 prime, you are again going to get exactly this term which will cancel out, and you are going to be left with this term which is there already on the left hand side. So the left hand side here is a total derivative. It's a derivative of a function. Of course, if the derivative vanishes, this immediately leads to psi2 psi1 prime minus psi1 psi2 prime being a constant. By the way, this should not surprise you at all. This is nothing but the Wronskian of the differential equation that we are writing down here. And this is a result which you should be pretty familiar with from the theory of differential equations. But what is important here is that if we are dealing specifically with bound states, what happens is that the wave functions have to vanish at infinity, which means that if you go very, very far away, psi2 and psi1 both vanish. In fact, so do their derivatives, of course, because otherwise you will not get a vanishing psi2 psi1 at infinity. But anyway, what you end up with is that the left hand side vanishes when you move very, very far away from the origin. But since this is a constant, it means that if it vanishes very far away from the origin, it has to vanish everywhere. So this has to be 0. Notice that this works only for bound states, because only for bound states do psi1, psi2 go to 0 as mod x goes to infinity. Now, if the constant on the right hand side is 0, then it's very easy to show that all you are going to get is psi2 psi1 prime has to be equal to psi1 psi2 prime, which means psi1 prime by psi1 has to be equal to psi2 prime by psi2, and that leads easily to the result that psi2 by psi1 is a constant. Just plain integration, this gives you log psi1, this gives you log psi2, and you get log psi2 minus log psi1 is a constant. Now if psi2 by psi1 is a constant, that contradicts our starting assumption that psi2 by psi1, this ratio is not a constant. That's your contradiction, and that shows that the assumption that there is a degeneracy for 1D bound states must be wrong, and hence establishes our result. Why does this argument not work for 3D? The answer is simple. In 3D, if we start with the same assumption, what you end up with are these two equations, which are very similar to what we had before, except that Laplacian replaces the second derivative. Playing the same game as before, multiplying the first one by psi2 and the second one by psi1 and subtracting, we end up with this result. Psi1 Laplacian psi2 minus psi2 Laplacian psi1, or the other way around, is equal to 0. Now once again, this expression on the left is pretty familiar to all of you from elementary vector analysis, and I'm pretty sure all of you know that this is a divergence. Just like the 1D case, psi2 psi1 double prime minus psi1 psi2 double prime was a total derivative, this one is a divergence. Is the divergence of psi2 grad psi1 minus psi1 grad psi2 equal to 0. Now if I could have argued from here that this vector here, the vector which is the argument to the divergence, because it has zero divergence, it's a constant vector field, then I could have easily said that this vector field must vanish infinitely far away for bound states, and hence the constant has to be 0, and psi2 grad psi1 must be equal to psi1 grad psi2, and from there it's pretty easy to see that you would end up with exactly the same contradiction as before. However, divergence A equal to 0 does not imply that A is a constant vector field. As you all know, there are plenty of non-trivial vector fields which can have a divergence of 0. Of course, such vector fields are called solenoidal vector fields, and any vector field which is a curl of another is of course an example. So you can have a situation where the vector field of course vanishes infinitely far away, but is very non-trivial and complicated at other points. In other words, psi2 grad psi1 minus psi1 grad psi2 does not have to be 0, and hence psi1 by psi2 equal to constant no longer follows, and you no longer have a contradiction. So in 3D, it's very possible for bound states to be degenerate. As you know, there are plenty of examples. All the hydrogen atom energy eigenstates for n equals 3, for example, all of them have the same energy and they are degenerate. That is why our result works only for 1D, and in 1D we are forced to conclude that for a parity symmetric Hamiltonian, the energy eigenstates will be even or odd. In 3D, we can choose them to be even or odd. Before we go any further to look at various properties of the Schrodinger equation, and in particular how these properties affect the behavior of the wave functions that we have just studied for the harmonic oscillator, let me take help of software once again. What you see here on the screen is a part of a code that's pretty straightforward to write. As you can see from the top, this uses various Python modules, in particular NumPy, matplotlib, and scipy. All of these should be pretty familiar to you from previous courses, except perhaps the matplotlib.widgets thing here. All that I'm using this for is essentially to give me a slider, which I can put in my graph so that if I move the slider with my mouse, I can actually change the value of a variable. So let me just try to explain what this program does. This actually solves the equation psi double prime plus lambda minus x square times psi equals 0, this second order differential equation, starting from an initial condition that psi is 0. Well, it should be at minus infinity, but we are not going to handle minus infinity here. It's going to be at some large negative value, let's say minus 5. And then we are going to try to integrate this differential equation to find out the wave function not at plus infinity, which is what you really should be doing, but at plus 5, let's say. Well, 5 is just a convenient number I have chosen for this code. I could change this, make it larger and get a more accurate result perhaps. And all I am doing is I am taking an arbitrary value of lambda, calculating the integral using scipy.integrates ODEInt function, which we are going to discuss in some detail later in the computational class. And I'm just using matplotlib to plot the result. So although this may look a bit long, there's roughly some 50 odd lines to this particular code, but frankly all the work is really getting done in these few lines. The rest is just sort of set up for the slider and the canvas and so on. Sort of bells and whistles which makes the thing look good. Okay, let's try to see what this will do. Let's try to run this using Python. And this is your result. So what I have here is a slider which I can slide to change the value of energy. Here what I'm calling energy is really not the energy, it's lambda, which of course is proportional to the energy. And as you can see, I've taken some value of lambda, which is now 0.099, and I've started integrating the differential equation starting with the initial condition of 0 on the left hand side, and as you can see, it's diverging rather badly. Now, as I keep on increasing the energy, take a look at what happens to the wave function. This is of course why I use matplotlib. I can dynamically change the graph this way, and notice that now the wave function is still diverging. We are at 0.92, but it's showing some hope of converging. In fact, if I actually were able to do this very carefully, I would see somewhere between diverging to plus infinity, as it was before, and now diverging to minus infinity, the wave function had actually gone through a 0 at this end. This is at the heart of what is called the shooting method in quantum mechanics to find out energy eigenvalues. But now, if I keep on changing the energy further, take a look at what happens to the wave function. It now flexes again, and what was going off to minus infinity is now coming up, and now it just crossed. Okay, it just crossed the axis again, and somewhere in between, somewhere close to 3, as this is telling you, you actually manage to find the next wave function. And this wave function, as you could see, is an odd function, as we had seen earlier. But what's also important is that this node, if you carefully see, in fact, let's take a look at what happens to this 0 crossing as I move on and go closer and closer to the next energy eigenfunction. Notice that at this stage, the wave function starts to flex again and is coming down. But what has happened is that this extra 0 crossing is now going to serve as a node for my new wave function. So once again, you have a 0 crossing here, and not at plus infinity, simply because you have crossed the value 5. You should notice that this is a very sensitive thing. Shifting this very slightly also makes this very, very different. So as I keep on moving the slider, you can see the solution going through various energy eigenfunctions, and each time adding a new node, and you can also see the even and odd character of this. Of course, if I move this slider much more carefully, you should be able to see that it's getting closer and closer to vanishing on the other side as you get close to all the odd integer values for this energy or lambda parameter. In order to look at this quantization thing in a bit more detail, let me just go back to the code and just change the range of the slider. Instead of going all the way from 0 to 20, what I'm going to do is just let the slider go from 0.999 to 1.001. So we are going to stay very close to 1 and see what happens. And what I'm going to do is also change this format for the printout for the value of the energy on the side so that it shows 7 decimal places. That's what the %.7f really is doing. So let's run the code now and see what happens. Okay. Now you see that because I've started at a value of 0.9992, the wave function is almost trying to converge, but it's still blowing up. Now let's see what happens as I slowly change the energy. Now you can hardly see anything happening to the wave function now, but now keep looking carefully. As I keep on increasing the energy or the energy parameter, the diverging part of the wave function slowly comes down, and now it's rapidly going to go through 0. But if I'm very, very careful, Okay, I have to be very, very careful here. Yeah, just done it. Just managed to match the other side. And you are getting 6 9s followed by a 7. You expect this to happen at exactly 1, but there are 2 reasons why that's not happening. One, I'm using a numerical calculation and there are errors in numerical calculations. And 2, I'm not actually using the boundary conditions that the wave function vanishes at minus infinity and plus infinity. I'm actually using boundary conditions that the wave functions vanish at plus minus 5. So this is like putting a harmonic oscillator between 2 hard walls at plus 5 and minus 5. Now, because the width of the Gaussian is of the order 1, and if you get to plus minus 5, the wave function is going to be very, very close to 0 anyway, even for the exact Gaussian. It hardly makes much of a difference. But if you cross this and go further, notice that as the energy changes, the wave function rapidly moves away. Let me just show you one more example of this particular code at work. Here I've started with the energy very close to 4.999, in fact very close to 5, and I've also changed the parameters in such a way that moving across the entire slider is going to change the value of the energy by a very, very small amount. And you can see what's happening. As you get closer and closer to 5, if you're right around here, you have managed to get the neat second excited state. That is the one which corresponds to n equals 2 and hence lambda equals 5 of the harmonic oscillator. And as you move further, of course, the wave function starts diverging again. So the lesson that you can learn here is that quantization essentially happens because while I can solve the differential equation perfectly well for any value of lambda, only for certain values of lambda will the wave function not blow up, which of course is the same as the lesson that we learned algebraically in the first lecture. At the very beginning, you also saw that the number of nodes keep on increasing as you go higher and higher up. And apart from the algebraic understanding of this that we had earlier obtained from the properties of the Hermite polynomial, this visual picture that I gave you a while ago, that the extra zero crossing turns into the next node, that actually is one other way of understanding why you get one more node every time. As we have just seen, the number of nodes that the energy eigenfunctions have keep on increasing with energy. Now that is sort of easy to understand by seeing what happens as the energy changes to the differential equation. But is there some deeper mathematical reason behind it? And it turns out there is. In fact, this is called the Oscillation Theorem, and we are now going to prove this. So what does the Oscillation Theorem really say? It says that if psi1 and psi2 are two energy eigenfunctions belonging to eigenvalues E1 and E2 respectively, where E2 is more than E1, so psi2 corresponds to the larger of the two energies, then between any two nodes of psi1, the one corresponding to the smaller energy, there is a node of psi2. So between any two nodes of psi1, there is a node of psi2. So what does this really mean? It sort of means that if you have a wave function psi1 like this, where psi1 has nodes here and here. So this is the horizontal axis, the psi equal to 0 axis, so to speak. So let's say there are nodes at the points A and B. What we are claiming is that psi2, which is the wave function corresponding to the higher energy, must have a node somewhere in between, must cross the 0 somewhere in between, either going from top to bottom or going from bottom to top. But there has to be a 0 crossing somewhere in between A and B. That is what the oscillation theorem tells me. So how do we prove the oscillation theorem? Once again, the proof is simply by contradiction. That is, you'd simply assume that this is not true. Let us assume that between two such nodes A and B of psi1, there is no node of psi2. So psi2 is either positive throughout or negative throughout in that region. For the sake of definiteness, let us just assume that psi2 is positive throughout the region And also assume that psi1 behaves like this, that it has a node at A, before which is negative. As x crosses A, psi1 becomes positive, then it becomes 0, that is, reaches a node once again at B, and then becomes negative. Now, of course, you might wonder what would happen if instead of behaving like this, psi1 had behaved the other way. Or if instead of being positive throughout the interval between A to B, which we have assumed and which we are going to contradict, if we had assumed that psi2 is negative throughout in that interval. As it should be pretty easy for you to verify, the final conclusion, that is that this will lead to a contradiction, will be there no matter which one of the assumptions you make. So I'm just going with this one, just to be definite. Just think about it. You should be able to figure out why a similar line of arguments will lead to a contradiction in all these other situations as well, as long as we assume that psi2 has a fixed sign for the whole interval. Now, of course, as always, we will have to start with the Schrodinger equation. So this is the Schrodinger equation for psi1, and this is the Schrodinger equation for psi2. Now you have two different energies, E1 and E2. So just as we did for the no-degeneracy proof, what we will do is we will multiply the first equation by psi2, the second one by psi1, and subtract. So I'm going to get psi2 psi1 double prime minus psi1 psi2 double prime on the left hand side. However, I will not get this thing equal to 0 because of the fact that these two equations are for two different energies. So what I'm going to get is this. Of course, what we will use is the fact that, as we had seen earlier, this is a total derivative. So this really is the derivative of psi2 psi1 prime minus psi1 psi2 prime, which means integrating this should be pretty straightforward. So let's just integrate both sides with respect to x. If we integrate the right hand side with respect to x, what you are going to get is simply integral of psi1 psi2 dx from A to B times this factor twice m by h cross square E2 minus E1. On the right hand side, you are simply going to get psi2 psi1 prime minus psi1 psi2 prime evaluated at B minus the same quantity evaluated at A. Now, according to the assumptions we have made, psi1 is positive in the interval between A to B, and psi2 is positive throughout in that interval, including at the two endpoints. So this integral is positive because it's an integral of just positive numbers. On the other hand, E2 minus E1, this factor is also positive because we are considering psi2 to be the energy eigenfunction corresponding to the higher of the two energies. So this is a positive quantity. So the left hand side of this equation is positive, definitely. What about the right hand side? The first thing to note about the right hand side is I don't need to worry about this term at all because psi1 at A and psi1 at B are both 0, A and B being the nodes of psi1. So this term vanishes anyway. So we are only left with this term at B minus this term at A. Now psi2 at B and psi2 at A are both positive. But what about psi1 prime? According to my picture, psi1 is an increasing function at A and a decreasing function at B. What that means is psi1 prime is positive at A, negative at B. So this thing that we are evaluating is actually negative at B, and from that we have to subtract its value at A, which is positive. Hence, the right hand side is definitely negative. So this is where we end up with a contradiction. The left hand side is always positive and right hand side is always negative under these assumptions. You can easily see that if I were to change psi2 and assume that it's negative throughout, even then you will get a contradiction. Then the left hand side will end up being negative and the right hand side will end up being positive. The same goes for the situation when we assume that psi1 has nodes at A and B and is negative throughout in between, as opposed to what we did here. Again, you can easily convince yourselves that you are going to get a contradiction. The only way to get out of this contradiction is to assume that psi2 must change sign somewhere in between A and B, and what that means is that it has to go through 0 somewhere in between. So there has to be at least one node of psi2 in between A to B interval. A moment's thought should convince you that this theorem actually implies that psi2 will have more nodes than psi1. Why is that the case? Well, if you think of psi1 having this particular wave function, so there is a node here and a node here, and maybe a node here, psi2, the one corresponding to a higher energy, must have nodes, at least one node between these 2 points, another node between these 2 points. But in addition, psi2 must also have a node between this point and infinity. Both are zeros of psi1, although this is the one point which we consider to be a node. This one we don't really count as a node. But the argument works whenever psi1 vanishes, so it will also imply that you have to have a node here and another node here. If this is the last node before minus infinity of psi1, psi2 must have a node somewhere in between. Of course, psi1 and psi2 both will vanish at negative infinity on this side, and so will psi2, but you will have at least one more node of psi2 than psi1. Of course, because we have not said that psi2 is corresponds to the next higher energy, all we have used in this theorem is E2 is more than E1. There is really no guarantee that in between any two nodes of psi1 there is exactly one node of psi2. So all you can conclude from this is that psi2 will have more nodes than psi1. At the very least, it will have at least one more node than psi1.